Hello everyone, and welcome back to this series on real analysis. Today we're going to be discussing a very important topological aspect of sets, and that is known as compactness of sets. So, let us briefly introduce a couple concepts that we're going to need in order to, more easily define what does it mean for a set to be compact. So let's assume that we have a subset of the set of reals. Then we're going to define this term an open cover of that set A. So what is an open cover? So an open cover is just going to be a collection of open sets, and I'm going to be representing it by fancy letter O to be the collection, and then we're going to have a bunch of sets within that set in R whose union contains A. So we can write that as what? So A is going to be an element or a subset thereof of the union of all of those open sets. So we can write that A is going to be a subset of the arbitrary union across all A of those particular open sets O. Right, so O and alpha. And here alpha could be enumerated over a countable or potentially uncountable set if you desire. So let's just go over just a quick numerical example just to make sure we understand exactly what an open cover of A is. Let's just use a basic example. Let's assume that A is equal to the half open interval 5, 8. And let's assume, of course, that that is the subset of R. So what does that look like geometrically? So we're going from 5 and we're going to 8. Closed circle at 5, open circle at 8. And it's going to be every point in this particular region, right? So, what is an example of an open cover? So we can define one open cover, the first open cover, to be equal to the open interval for 8. So keep in mind an open cover is a collection of sets, in particular open sets. So this is obviously an open set. If I go from 4 to 8, notice that every element within A is also within this little baby set, let's say normal 01. So therefore this is an open cover of A. And there's obviously infinitely many open covers that you could build. For example, I could also do for infinity. For infinity is also an open set, and closed interval 5 to 8 is a subset of that little baby set for infinity. Let's be a little bit more fancy with it. Let's go 4 to 6, 5 to 7, and 6 to 8. So what exactly are we doing here? So we have our 5 to 8 region, and what we're going to do is we're going to open interval this, and then we're going to open interval that, and then we're going to open interval that, and then we're going to open interval that, and that, and that, and so on. And pretty much as you can see, if you unionize all of those open intervals, then everybody within 5, 8 will be located there. A very important characteristic is that the distance between 4 and 6 is equal to 2. If you were to do 4, 5, 5, 6, and 6, 7, that would not be an open cover because the point 5, 6, and 7 would not be in the union because you cannot unionize open intervals that are disjoint and get those boundary points, right? So we can actually easily generalize this set or collection O3. Let's call it O4, and you can say that this is a open cover in the form n minus 1, n plus 1, where n is a natural number. So this is pretty much a generalization of the collection O3. Right, and obviously since that includes O3, and O3 is an open cover, then we also see that O4 is also an open cover. More importantly, this is a collection, a finite collection of open sets, so it's a finite cover, whereas this also is an open cover, but it's an infinite open cover. So now let us, once we have this, define the next important concept. So definition number 2. So suppose that O is an open cover of A and O prime a subset of O. That is, it's some open sets, but not all of them that could be potentially in O, with also O prime also an open cover of A. then this O prime is called a subcover of O. Pretty much it's just a fancy way of saying, O prime is a subset of O. O is an open cover of A. O prime is also an open cover of A, so we say that O prime is a subcover of O. So it's a fancy subset, I guess you could say. So once we have this, let's see if we can build some subcovers of sets. And let's again choose the same exact example, A. So let's take A to be equal to 5 infinity, and again let's subset that in the set of reals. So if we take our fancy open cover of A, in particular n minus 1, n plus 1, such that n is a set of naturals, and we choose O prime to be equal to 4, 6, 5, 7, and then 6, 8, right? So we can clearly see that O is an open cover of A, and we can clearly see that this set is a subset of O. So from these two particular things, we can clearly see that O prime is a, more in particular, finite subcover of A. Right? So that pretty much is what we have, and not of A, but of O. Right? So we have subcovers, we have open coverings. Now let us introduce the main concept that we're going to be focusing on today. All right, so definition number 3. So this is the superstar. So a set A, subset of R, is said to be compact if every open cover of A has a finite subcover. So some important words that we need to focus on here. So it's compact if every open cover of A has a finite subcover. Right? So let's sort of think about this set 5 infinity. We have found a particular open cover of A, this n minus 1, n plus 1 type of structure, right? But that's not an arbitrary open cover, that's a particular open cover. But for that particular open cover, we were able to find a finite subcovering of that particular set. But we have to show that this set has, for every open cover of it, a finite subcovering of it. So it's very, very more broad, to be precise. So let's look at a little bit more of a specific type of set. So question, if A is bounded, which our little example from before indeed is it compact? If a set is bounded, does that mean it is compact? Because if it is, then we can take as corollary that half open interval 5, 8 is a compact set. So let's actually take a very important interval. Let's consider the full open interval A 0 to 1, which is obviously bounded above by 1 and also bounded below by 0, amongst other numbers. So what I want to do is I want to consider a particular open cover of A. So I'm going to let this open cover be the set of all intervals 1 over m, 1 minus 1 over m, such that n belongs to n greater than or equal to 2. You might think this is kind of weird. For example, why do I take n to be greater than or equal to 2 in the set of naturals? Well, if n is equal to 1, then we have 1 over 1, comma, 1 minus 1 over 1, which is 0. And 1, 0 doesn't even make any sense because it's not even listed from least to greatest. When n is equal to 2, we're going to have 1 half and 1 half, which is obviously going to be equal to the empty set. And that's not very interesting as well. I mean, it is bounded, but that's a little more of a special case. You know, is the empty set compact? The answer to that is going to be yes once you sort of convince yourself of that, but I don't want to consider that special extreme case. So by the time we hit n is equal to 2, then we have 1/2 and then 1 minus 1/2. So that's the n is equal to 2 case. And then what we want is n is equal to 3, so that's going to be 1/3, and 1 minus 1/3, that's going to be 2/3. And then we're going to have 1/4, 3/4, 1/5, 4/5, and so on. So what we're actually going to look at for this particular set, and actually I actually want to include that empty set just for fun. So pretty much these intervals are kind of symmetric about 1/2 since they're symmetric in the interval 0 to 1. So over here we're going to have 1 over m. Over here we're going to have its complement if you view it from the perspective of probabilities. So we have this open interval, and what's going to happen? So this interval is going to push outwards to 1, and this boundary is going to push out to 0. So is this an open covering of A? So pretty much what you need to show is for any x in 0, 1, does there exist a natural number bigger than or equal to 2 such that there exists at least a union of intervals for which that x is contained within? Okay, so you should be able to prove, at least from the things that we've built before, that O is an open cover of A, since, and then comes a little calculation portion, n is equal to 1 to infinity, 1 over m to 1 minus 1 over m, and that should start at 2, is equal to 0, 1, and obviously A is contained within that. Right? So now we have an open cover, so is it compact? So if it truly is, for any open cover, in particular this one, we should be able to find a finite subcover of A that is contained within it. So I have these intervals, infinitely many of them, and I need to choose a finite subset. So if we take a finite subset of O, let's call it O prime is equal to the set of all intervals of the form n, let's do 1 over n, and then 1 minus 1 over m, where n is an element, let's say n1, n2, all the way down to n capital N, where capital N is, of course, a natural. And we choose, because that's a finite sequence of real numbers, choose, let's do n star to be equal to the maximum of this set here. So the maximum of n1, n2 down to n capital M. Then what you have here is that each of these, so each 1 over n, 1 minus 1 over n, is contained within 1 over n star, 1 minus 1 over n star. So when you look at this geometrically, I don't care how big that n star is. If we go from 0 to 1, this n star is still not going to be containing all of the values within 0, 1, because we're always going to be missing these particular objects, right? So we can clearly see that the infimum of that set is 1 over n star, and the supremum is 1 minus 1 over n star. And clearly we can see that 0 will be less than the infimum of this 0 prime, and that's strictly less than the supremum of 0 star, and that's strictly less than 1. Right? So from this we can clearly see, both from the picture and the supremum infimum perspective, that there exists, that means there exists an x within 0, 1 that does not exist here. Not exist here. In particular, you can choose x to be equal to 1 plus, let's say, the upper bound, 1 minus 1 over n star all over 2. That is, you can choose the midpoint of this particular interval, or you can choose a point in the midpoint of that left boundary interval as well. Right? So keep in mind, this is an arbitrary subcover of O that is finite. So that includes pretty much every single one of them. Right? So therefore, we have a particular open cover that does not have a subset O prime that is finite that also contains A. That is, it doesn't have a finite subcover. Now, does this mean that you can't find an open cover of A that does have a finite subcover? No, that's not what this means. It has to be true for every open cover, right? So it's almost a construction proof if you're trying to show that this set is not compact, right? So therefore, 0, 1 is not compact, right? So sad day for 0, 1. So what can we conclude from this very basic example? So that means that boundedness is not enough, it's not sufficient enough for compactness. So is there any other properties for sets that might help us guarantee that a set is indeed compact? So far we have that boundedness isn't enough for compactness. So every bounded set is not necessarily compact. So another natural question you could ask is, well, what about closed sets? Is every closed set a compact set? Let's look at a particular example. In particular, let's consider the set R, which obviously is closed and also open, but R is not bounded. We already see that bounded isn't really necessary, at least from our exploration so far, to conclude, enough for compactness. Well, what about closedness? So let's see if we can build an open covering of R. So let's actually choose the same open cover as before, in particular minus n to m, such that n is a natural number. So is this really also an open covering of R? So for any x in R, you should be able to show that there does exist an n in the set of natural numbers such that x belongs to minus n to the m. Right? So if this is the case, then what can we say? So what we need to do is we need to take an arbitrary subcover of this that is finite and show, if we want to show that it's not compact, that R is not contained within it. So let us take O prime to be a subset of O with O prime finite. All right. So in particular, let's assume that O prime is of the form minus n1, n1. Let's do minus n2, n2, all the way down to minus nn, nm. Right? Obviously, n in the set of naturals. And as usual, just like before, we're going to take n star to be equal to the maximum of these n's, n1, n2, all the way down to nm. And obviously, we see that all elements of O prime are subsets of minus n star, right? But what can you tell me about that finite subcover? So, but this set n star plus 1, so let's go one more than that because what we have here is an open interval. If we go one more number bigger than n star, we know that this number does belong in R. So what does that exactly mean? So that means this object does not belong to O prime because it's in the complement of that open cover. So since we have a number that belongs to R but does not belong to the finite subcover of this open covering O that we have built, then we have what? That means O is an open cover of R that does not have a finite subcover of R. That is, since you have R, you need infinitely many subsets of O in order to cover all of R. So that means what? That means R is not compact. Right? So that's kind of sad for the set of reals. Okay, so boundedness isn't enough, closedness isn't enough, so what else can we say? So maybe we can work a little bit backwards to sort of see, well, if it is compact, does it have any properties that may interest us? And that's where the next and very important theorem comes into the picture. Let's assume that A is a subset of R such that A is compact. Then one can show that A is both closed and also bounded. So that's actually pretty nice. So if A is compact, that means it's both closed and bounded. It's both. That's pretty cool. So let's see if we can go ahead and prove this. And you might want to pause the video to sort of see if you can do this. So what I want to show first that this set is indeed bounded. So let's go bounded first. So let's assume that let n be a set or an element of the set of natural numbers. And let's define a nice little set, Sm to be equal to minus n to m. Right? So keep in mind, what are we assuming? We're going to be assuming that A is a compact set. So we're defining n to be in the set of natural numbers, and we're defining this open interval minus n to m. And we're going to let O be equal to the set containing all of those intervals minus n to m. So it's almost the same exact sequences of intervals that we've been using to contradict compactness for the other ones. Right? So we have already, in some sense, shown that O is an open cover of R. Right? And we know that A is a subset of R by definition. So that means what? Then that means that A is a subset of the union across all K of these SKs, right? Because keep in mind, that is equal to R from K is equal to 1 to infinity, right? So that much we already know. So now let's use that assumption that we have. So since A is compact, and we have that A is a subset of the union of all of those open sets, that means what? That means O is an open cover of A. So that means O is an open cover of A particular one. That means, since it is compact, every open cover has a finite subcover. So we can choose a finite subcollection from the set O, and A will still be contained within it. Right? So that means there exists a capital N in the set of naturals such that A is a subset from the union from K is equal to 1 to M of Sk, and that by definition will be equal to S capital M, which is going to be equal to minus capital N to capital M. Right? So A is a subset of this set. Right? So we clearly see that Sn is bounded. So therefore, since Sn is bounded, and that's capital N, and A is a subset of S capital N, that means A also is bounded, right? Because if you're a subset of a bounded set, that means you are bounded by, the bounds of that set that bounds you, okay? So if A is compact, then it is bounded. We can clearly see that. So we see that compactness implies boundedness. Compactness implies boundedness, right? And obviously, the theorem states that compactness also implies closedness, and I will leave this for you to sort of practice on. So if compactness implies boundedness and compactness implies closedness without the reliance on boundedness, that means compactness implies both of them simultaneously, right? So that's actually very, very of a beautiful result. So compactness implies closed and bounded, right? So a nice natural question, what about the other direction? What about the other direction? Because we've already shown that closedness is not enough to prove compactness. We've already shown that boundedness also is not enough to prove compactness. But if we have a set that is both closed and bounded, does that imply that the set is bounded? You might want to pause and think about that statement for a moment. So the next theorem confronts this particular question, and this is sometimes associated or called the Heine-Borel theorem. And it says that a set A, subset of R, is compact, take a guess at what the next statement is, if and only if A is closed and bounded. Right? So yes, it is indeed true. Right? So we've already shown that compactness implies boundedness, and obviously you can show that compactness implies closedness, but also, so pretty much all you would have to show now, so this proof would just require you to show that if you have closed and bounded, then you can get compactness from that. And again, if somebody says, oh, does closedness, is that enough? No. Is bounded enough? No. But if you have both of them, indeed, yes. And again, this proof is a little bit more involved, but I'll let you see if you can figure that out. But once you do, it definitely is involved, but definitely satisfying if you can get it on your own. So now we have the Heine-Borel theorem that says if you can show that a set is both closed and bounded, it can be viewed also as compact simultaneously without having to show the open cover, finite subcover type of proof for it. So it does give us a different way to show also closed and bounded if you can just show, every open cover has a finite subcover. And that's actually very, very beautiful if you can show that. So what are some compact sets that you definitely should know? So the most, smallest of the compact sets that you could consider is the empty set. So one should be able to show that the compact set is, or the empty set is compact. Is the empty set bounded? Trivially so. Is the empty set closed? Yes, we've already shown that. So by Heine-Borel, we see that the empty set is indeed a compact set. So if we consider the closed and bounded interval AB with A, B, and R, obviously a closed interval is a closed interval, and that closed interval is bounded above by B plus 1 and below by A minus 1. So you can clearly see that this also is a compact set as well. Some more general properties, I guess you could say. Let's assume that you have A and B compact sets. Then let's go A. The Cartesian product of A and B, the union of A and B, and the intersection of A and B also is compact. And the proof of those is actually pretty easy to do because we've actually already proven several properties about the closedness and boundedness of unions, intersections, and Cartesian products. But there is one thing that you probably should consider on your own is the generalization of these results. So if you have a countable collection of compact sets, will their union be also compact? What about an uncountable union of compact sets? What about that? And you could consider that also in the realm of Cartesian products and intersections as well. Now, one more practical example that is used in so many proofs in other courses is the following one. And let me briefly spell this out just in case you aren't familiar with the notation. Let's assume that X and C are elements of Rm. So now we're not really talking about real analysis anymore. Now we're talking about real to the power of n, the Cartesian product of R with itself n times analysis. And also let's assume that R is a positive real number as well. So what I want to do is I want to define a function between X and C to be equal to the square root from the sum from k is equal to 1 to n of xk minus ck, the quantity squared. So if you've ever taken linear algebra or vector calculus, this idea should make sense to you, because what exactly is x and c look like? Well, x looks like, x1, x2, all the way down to xn, and c similarly. So if we take, for example, n is equal to 3, then what you're actually going to have is potentially a sphere, all right? So if we take a point in the middle, let's call that C, that's the center of the sphere, and we take an arbitrary point on the surface of the sphere, and let's call that x, and let's consider the distance between C and x to be equal to r. And how would we define this particular set? So what we can do is we can define the set B, centered at C with radius r, to be the set of all x in Rm, such that the distance between x and c, is less than or equal to r. So it's not just the points on the boundary or the surface of the sphere, it also contains all the points within the sphere as well. So you should be able to see that this closed ball or this closed sphere also is a compact set. So one can show that B, CR, is compact, right? My colors switched for some weird reason, right? So we have these 4 very important examples of compact sets. Are they the only ones? Of course not, but the provability of them being compact is very, very trivial if you consider, the Heine-Borel theorem. Just show it's closed, just show it's bounded, and then we get it from Heine-Borel. So now let's consider a more practical question. So is working on compact sets a good thing? You can probably start thinking, yes, of course. So let's assume that we have a function that maps, say, A to B. And let's suppose, for the sake of conversation, A is compact, meaning it's closed and bounded. And let's assume that F is continuous on A, all of it, including its boundary. And let's assume that A is differentiable on the interior of A. So if you have these properties, then what can you say? Well, we have the mean value theorem to give us values, which is associated to differentiability. That means there exists a C in between the lower and upper bounds such that the derivative is equal to the average rate of change about the boundary points of that interval. You have the extreme value theorem, which means that this function attains its maximum minimum value on this domain. Since we have a closed and bounded domain, we also have that the image of A under F will also be bounded as well, and that can be viewed as a subcorollary of the extreme value theorem. And also, since F is continuous on a closed and bounded interval, you should also be able to show that we've shown before that F will be uniformly continuous on that domain set as well, right? So although we have proven mean value theorem, extreme value theorem, FA bounded, F uniformly continuous on A, without the idea of compactness, compactness gives us another perspective or another set of tools that we can use to verify such properties, right? So let us state a very conceptual question that one might be asking by this point. So if we've already proven these theorems that are quite useful, especially in calculus and other realms of mathematics, but we didn't even mention compactness when we proved them, we just worked with theorems that we already had from properties of closedness and boundedness of sets in R. And compactness is equivalent to both of them being true, then why do we even need to discuss compactness? It's a natural practical question from the theoretical end, right? So let's briefly think about this, and you might even want to pause the video and think about this for yourself. So let's assume that we have something to prove, right? We're trying to show that, what do we need for this function to have an extreme value? What does it mean to be differentiable? What does it mean, for its image to be closed and bounded under this mapping or something like that? So we can either prove that a set is closed, So how do we prove that a set is closed? Obviously, a more classical way to prove that something is closed is prove that its complement, our takeaway A, is open, right? And we have several theorems that can give us that. And let's assume that we also have to show that A is bounded, right? So pretty much what we need is we need to show that there exists, usually has to go with existence of bounded distance, right? So pretty much everybody within this set is relatively close to each other in the finite realm, right? And we have several theorems on how to show boundedness. But let's assume that those are the two things that we have to show. Instead of proving those two things, which can necessarily be easy if you're comfortable with them, you can equivalently just show that A is compact. Now, if you've already shown that A is closed and A is bounded, then we have that A is compact by Heine-Borel. But let's assume that you don't want to show that A is closed, or you don't want to show that A is bounded. So how can we show that A is compact? So the definition of compactness is what? That means every open cover has a finite subcover. So what exactly do you need in order to prove that every open cover has a finite subcover? So all you really need to understand is open and closed sets pretty well, and their properties under unions and intersections, right? And if you kind of think about it, open, closed sets, unions, and intersections, these are very abstract ideas that need not be only applied to R, or more generally, Rm. So if we want to talk about, what does it mean for a set to be closed and bounded in another world aside from R, compactness sometimes gives you a little bit more flexibility on how to show that they must be closed and bounded by proving compactness, because compactness only assumes, knowledge and comfortability with openness, closed sets, unions, and intersections, both finite and infinite unions and intersections, right? But of course, proving complements that sets are open, not always hard. Proving sets are bounded, not always hard. But compactness gives you a little bit more of an abstract view or an alternative view of showing that a set is closed and bounded. But keep in mind, by Heine-Borel, as long as you have a nice, beautiful space to work in particular R, then we have already discussed that compactness is equivalent to a set being both closed and also bounded as well. So that's just a brief expose into the realm of what it means for a set to be compact. In the set of real analysis, obviously, you can show that a set is closed and bounded and technically avoid any notion of compactness. But if you want to start to broaden the view and applications of real analysis into realms that sort of extend beyond the realm of R, compactness usually is a little bit more of an elegant way to do that. So I hope to see you once we discuss such elegant extensions, but until then, I hope you enjoyed this video. Take care.